Chapter 23, Discrete Random Variables, page 1. Part A, we're just going to talk about what is a discrete random variable. First of all, we talk about the discrete random variable, and then we compare that to the continuous random variable. The discrete random variable is a number that can take on whole number values. And two examples I'm giving here is like the temperature setting on an air conditioner unit. So like if you go around EAC, you might see some air conditioners set on 25, some on 24, some on 23, 22, maybe some set on 17, but it's always set on a whole number value. Okay? What else? IB score for MathSL between 1 and 7, whole numbers between 1 and 7. Okay, cannot be 1.5, for example. Okay, how does that compare to a continuous random variable? A continuous random variable is a variable that can take on number values like that are decimals or fractions, not whole numbers necessarily. Okay, so for example, the temperature outside. The temperature outside is going to be 17.3. It's going to be 25.6. Even if you had the right thermometer, you could measure it to much more precision. Okay, average time spent per day on IB MathSL homework. That's also a quantity that varies with decimal precision. Okay, it may be 3.56 hours or 2.4 hours. Okay, it's not going to be exactly a certain number of hours. Okay. How do you read this expression here? Probability of the random variable x, which is the capital X, taking on the value of small x, which is a value of x. Normally, when you write this expression, you don't normally write small x. What you normally write is like a certain number, like 7, something like that. The other thing that you might see is the probability, instead of the probability of x equals 7, you're going to have the probability of x is greater than or equal to 7, for example. Okay, we'll see more of that later. Number 1, classify the following random variables as continuous or discrete. So, the quantity of fat in a sausage. So that would not be necessarily a whole number, right? The amount of fat in a sausage, if you weigh it, is going to be, practically any number. So that would be continuous. What about C, the weight of a 17-year-old student? Also continuous, right? And we talked about this before. I mean, today's scales, they measure just certain values of weight. So it's like 60.2, 60.4. If you go to the drugstore, you'll notice that it doesn't even give you 60.1, for example. So it's not, with digital technology, you don't really see too many truly continuous measurements, but it is a continuously variable quantity. Okay. E, the number of trout in the lake. Okay, that's going to be a whole number, so that will be discrete. Right? And then G, the length of hairs on a horse. That is also going to, be decimal values, so we'll also put discrete. Number 2, for each of the following, identify the random variable being considered, give possible values for the random variable, and indicate whether the variable is continuous or discrete. Okay. So, in this case, to measure the rainfall over a 24 period in Singapore, the height of water collected in a rain gauge up to 400 millimeters is used. Okay, so in this case, the random variable being considered, which is the big X, is the height of the water collected in a rain gauge. Okay. 2, give possible values for the random variable. So this is going to be, it could be a decimal quantity, so it could be 43 millimeters, it could be 42.1 millimeters. Okay, so this is obviously continuous. Continuous. Okay. C, to check the reliability of a new type of light switch. Switches are repeatedly turned off and on until they fail. Okay, So in this case, maybe x would be number of times switch is turned off and on until it fails. Okay. Sample values would be 385 times or 462 times. Okay. And then is it discrete or continuous? It's discrete, right? Whole number values. All right. Consider tossing 3 coins simultaneously. The random variable under consideration is the number of heads that could result. List the possible values of x. So we got heads, 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 tail. It's really good to be organized about the way you write these out, because if you're not, you can miss one pretty easy. Okay, so I've written out 3 heads. I've written out 2 heads. Now I'm going to write out the 1 head possibilities. Do you see the pattern I'm following here? And then there's the 3 tails possibility. And so that's it. There's 8 possibilities. Tabulate the possible outcomes and the corresponding values of x. Okay, so we got here, we got 3 possible, or 4 possible scenarios. We have the 3 head scenario. We have the 2 heads, 1 tail scenario. We have the 1 head, 2 tail scenario, and then we have the 3 tail scenario. And so how many occurrences for each? Well, 3 heads, there's 1 occurrence, right? For 2 heads, 1 tail, there are 3 occurrences. Oops. Sorry about that. And then for 1 head, 2 tails, there is 3 heads. Or there's three occurrences. And then for 3 tails, there's also 1 occurrence, like for 3 heads. Find the values of p big X equals small x, or the probability that the random variable x takes on the value of x, the probability of each x occurring. Okay, so in this case, we're just going to arrange what we just wrote with this notation. So I'm going to do that offline, and then you'll see what it looks like. Okay, I'm almost done with this. What I've done is the probability that the random variable x takes on 0 heads, 1 heads, 2 heads, 3 heads is proportional to these numbers, 1, 3, 3, 1. But the probability that x takes on the value of 0 is not 1. It's actually 1 divided by the total possible number of outcomes, which we know is 8 from looking at this list here. So actually each one of these is going to be a fraction with an 8 denominator. So I'm going to write the 8 denominator for each one here. Okay, and does it make sense that all these outcomes, probability outcomes added together, should add up to 1? Okay, so this is the answer for C. Then it says to graph the probability distribution against x on a probability column graph. So let's do that. When you do this, try to use a ruler to be neat. Unfortunately, on this technology, I can't use a ruler. So I'm going to have 4 values. I'm going to have the 0 value, the 1 value, the 2 value, and the 3 value. And for each one, I'm going to have a column here. So 0 is going to have a height of 1. 1 is going to have a height of 3/8. Oh, I just did something wrong. I wrote 1 and 3 instead of 3/8 and 1/8, right? Sorry about that. It's a common mistake though, right? Okay, so this is the probability, and this is the random variable x. Okay, so that's what it should look like. Now let's move on to page 2. 23b. If x is a random variable with sample space x1, x2, x3, all the way to xn. Now those are the possible values for x. And if you've noticed, now we're starting to talk about discrete random variables, which is the title of the chapter. We're no longer talking about the continuous random variables that we mentioned above. The reason why we mention the continuous random variables is so that you don't think that the study of probability is only about discrete probabilities. We also study continuous probabilities, but in this class we are not going to talk about continuous probabilities except from the case from the point of view of normal distributions in the next chapter. Okay, so the different values that can be taken on are represented by this set here with a bunch of small x's and subscripts, but that could, for example, it could be the variable of the temperature setting on an air conditioner on a UC campus. You're going to find the numbers between like 17 and maybe 35 or something like that. And the corresponding probabilities are P1, etc., all the way to P subscript n, so that the probability of the random variable x taking on a value xi, x sub I equals P sub I. Okay, and that is a pretty complicated expression, but the only thing it's saying is basically this. Okay, so there is a set, and in this case, for the coins, or for the coins, the set is 0 heads, 1 heads, 2 heads, 3 heads. Each one of those has a corresponding probability, a number between 0 and 1, in this case 1/8 or 3/8. Okay, so if you would write this as in this form, what you would say is, oh, I have in the sample space, I have 0, 1, 2, 3 heads, right? And in the probability, the probabilities that correspond to that, I have 1/8, 3/8, 3/8, and 1/8, right? Because that's the correspondence is like that. Okay? All right. And the probabilities, if you add up all these probabilities together, like we said before, you get a total of 1. All right? So, let's move on. For example, when a coin is tossed twice, the number of heads, variable x, has sample space 0, 1, 2. Okay? So this is before we did when 3 coins are tossed simultaneously, right? In this case, we're saying when a coin is tossed twice. So instead of 0, 1, 2, 3, we have 0, 1, 2. So give the corresponding probabilities. It's going to be something like 1, 2, 1, like we discovered in our investigation. The probabilities in this case have a binomial distribution, and then we just need to divide by the total number of probabilities. So it's going to be like that. Okay. 3 ways to give the probability distribution of a discrete random variable. So 3 ways to display probability distribution are table, graph, and as a function such as a probability distribution function. And when you have a probability distribution function, what is the domain range? The domain is all the outcome values here. Remember, those are small x, and the range is the p-values, the probabilities for each outcome. Write down an expression for the probability that x is less than 3. So that would be something like probability is that big X is less than 3. Write down an expression for the probability that X is at least 3 but less than 7. Probability that big X is at least 3 but less than 7. Okay. Let's move on. Find X in these probability distributions. And so here we are just using what we just learned, that all the probabilities need to add up to a total of 1. So in this case we know that 0 has a probability of 0.3, 2 has a probability of 0.5, so K is the probability that 1 happens, which is going to be 1 minus the total here. So this is 0.3 plus 0.5, that's 0.8. 1 minus 0.8 is 0.2. So in this case, k has to be 0.2, right? Now, the next one's a little bit trickier. It has a bunch of k's here, but it only has one variable. And remember, we do know that if we add up all these, that we are going to get a we're going to get 1. So what we do is, we turn it into an algebra problem, because if we add all these up, we're going to get 1, right? So let's simplify this. K plus 2k plus 3k plus 1k is equal to 7k equals 1. So what is k? Divide both sides by 7, you get 1/7. Okay, so our k is 1/7. Not that hard. Explain why the following are not valid probability distribution functions. Well, I suspect that they don't add up to 1. Let's see. 0.2 plus 0.3 is 0.5, plus 0.4 is 0.9, plus 0.2 is 1.1. Okay, so that's why that's not a valid probability distribution function. What about this one? Ooh, this already looks bad. Whenever you have a probability, it has to be between 0 and 1. It cannot be negative 0.2. Okay? All right. Let's move on. 5. A dice is rolled twice. Draw a grid which shows the sample space. Suppose X denotes the sum of the results for 2 rolls. Find the probability distribution of X. Okay. So remember when we drew grids in the probability chapter to figure out sample spaces? So here I have a grid which is 6 by 6. Why is it 6 by 6? I'm assuming they're talking about a 6-sided dice. So I'm going to put all the let's say we got a red dice and we got a blue dice. So I put all the possible rolls that come out of the red dice, all the possible rolls that come out of the blue dice, and then the grid is a matrix of all the possible combinations of like red 4, blue 5, etc. So like every single possible combination that can happen. You can quickly look at the grid and note that there are 36 possible combinations that can happen, right? All right. Maybe I should say permutations because, okay. So that's part A. B. Suppose that X denotes the sum of the results for the 2 rolls. Find the probability distribution of X. Okay, so that would be, and we could show the probability distribution in a number of ways. Let's start with a table, okay? And so what are the possible sums of the 2 rolls? Well, and I'm going to zoom in for this. I'm sorry I didn't leave you much space. Okay, so obviously the highest sum would be this sum here, 6 plus 6, so it would be 12. And the lowest sum would be this one here, which is 1 plus 1 is 2, right? And then you could take on every single value in between the 2. And I really didn't leave enough space, right? Not even for me. Not even with my zoom capability. Okay, and then in between, you are going to have a number of different ways to sum up to each number. How many ways are there to sum up to 2? Just 1. How many ways are there to sum up to 12? Just 1. How many ways to sum up to 11? Well, 11, let's see. 11, it could be 6 plus 5, or it could be 5 plus 6. So that total is 2, right? By coincidence, the number of ways you could sum up to 3 is 2 plus 1 and 1 plus 2. It's also 2. Okay, what about 4? How many different ways are there to sum up to 4? Let's see, there is 3 plus 1, there is 2 plus 2, and there is 1 plus 3. What about the different ways to sum up to 10? There's 6 plus 4, there's 5 plus 5, and 4 plus 6. Do you see the pattern coming out here? I don't think I really need to do all of them, do I? What about the ways to sum up to 5? There is, and this is kind of interesting, there is no way to sum up to, so 5 would be 4 plus 1 and 3 plus 2, and 2 plus 3, and 4 plus 1, which is 4. And then different ways to sum up to 9. 6 plus 3, 5 plus 4, 4 plus 5, 3 plus 6. Okay? And so we can complete this now just by writing in the pattern here. We see there's 5, 5, and 6 here. And we can do one final check to make sure that, you know, what should this add up to? It should add up to 36 different outcomes. Okay? So if we add up 5 plus 4 plus 3 plus 2 plus 1, that's equal to 15. So that's 15. So that's 15. So that's 30, 36 with the 6 in the middle. Yeah, it checks out. Okay? So, yeah, they add up to 36. If I wanted to write the probabilities for each one, now I'm going to write, I'm going to write a 36 denominator for each number here. 1 divided by 36. 2 divided by 36. 3 divided by 36. 4 divided by 36. 5 divided by 36, etc. Right? Okay. And then finally it says to draw a probability distribution column graph to represent this data. And so, you know, sorry I didn't leave enough room again. Across the bottom, you are going to have the numbers 2 through 12, right? And the middle number is going to be the number 7. Okay. And then 7 has a probability of 6 divided by 36. Okay, and then the 2 has a probability of just 1 of 36. And then with the numbers in between, 3, 4, 5, 6, 3, 4, 5, 6. Each one of these is like kind of like growing, right? So like 3 goes up to here, 4 goes up to here, 5 goes up to here, 6 goes up to here, and in the other direction it's the same thing. Okay? Anybody ever heard of the dice game craps, which they play in casinos? In the dice game craps, the two critical numbers are 7 and 11. If you throw a 7 or you throw 11 on the first roll, you win. And you can see that the 7 is much more likely to come up than the 11. All right. 7. A discrete random variable x has probability distribution given by, and they give us a function. Remember we said that one of the possible ways of showing a probability distribution is with a function, and here there is one with a function. So find the probability that random variable x takes on the value of small x for all of these here. And so we're going to use the function to figure out each one. I think it's convenient to put this in a table, so I'm going to put 0, 1, 2, 3, 4. And those will be the possible outcomes, right? And then on the right side, I'm going to put the probability of each one. And how am I going to figure it out? I am going to use the calculator. I think the best way to do this is with y equals. Into y equals, I'm going to put the function, except I'm not going to put the k, because we don't know what k equals. So I'm going to put the rest of it. I'm going to put 1 divided by 3 to the x times 2/3 to the 4 minus x. 4 minus x. Okay. And then I'm going to look at the table of this function. And, oh my gosh, this is how you fix your table. Do you see how my table has like 0.35 and stuff? I just want integers in the table. So I'm going to say second table set. This is good to do on the exam if you messed up your calculator, you don't want to reset all the memory. I'm going to change the delta table to 1. And then I'm going to go back to the table again. There we go. Alright, and so we can see that the value for 0 is 0.19753, etc. Okay? So these are the values from 0 to 5 that you're going to write down here. And then you're going to find k and hence find this value. Okay, so let's write these values down first, just so you can see how I translate these values from the calculator to here. So we're going to have first 0.19753. 0.19753, and it's multiplied times k. Remember k? K was there, but I did not put it in the calculator, so it's just kind of a multiplier. And so I'm just going to copy the rest of these down. I'm not going to bother you with that. Now I want to figure out what k is, so what I'm going to do is I'm going to add up all these coefficients, and then I'm going to get this. The total of this is 0.38272 k, and remember that this should add up to 1. So I'm going to have 1 divided by that, and that's going to give me the value of k. K is 2.61. Okay, so k is 2.61. That is the first answer we're looking for here. And then we're going to use it to find the probability that x is greater than or equal to 2. The probability that x is greater than or equal to 2 is going to be the probability that x is equal to 2, probability that x is equal to 3, and the probability that x equals to 4. And we're going to add those three together and to see what we get. And so I just typed it all in here before, so I'm gonna use this part that I typed in before. I'm just going to erase the first part here, the first two. So I'm going to add up the numbers: 0.04938, 0.02469, etc. And then I'm going to get a smaller number. If I add these three up, it's going to give me a total of 0.08642 k. And so what is the probability that x is greater than or equal to? It's going to be 0.08642 k, because that's the total of the probabilities of x being 2, 3, and 4. And I'm going to divide it by the probability that, let's see, 38272 k. Okay, and then you notice that the k's cancel out, right? So all you're really doing is dividing this number by this number, and we get a probability of 0.226. Okay, and that's the answer for this part here. Okay? All right, and that's it for page 2.